Perfect. And the Zoom is on the top. But anyway, I'll begin. Dear Father, we thank you for this day, Lord. I thank you for these students. Just pray that you be with us today. Help us to just understand a little bit more, again, about sequences. And we just thank you for your grace and mercy for us each day. We thank you, Lord, that if we accept you into our hearts, that we have your righteousness in place of our own, which is worthless, of course. And we just thank you for your mercy to us this day, Lord. In your name I pray. Amen. I have homework 3 graded up here, which I'm just going to leave here. We can deal with that after class, I suppose. And here's the test 1 for those of you who didn't get it already. And I'll try to do that at the end of class. Just if you'd remind me about 3 minutes before class is done to do that, that'd be good. So go ahead and turn in your homework, if you don't mind. Thank you. All right, so let me start out. My goal here today is to try to walk us through some of the calculations and examples in section 11.4, which is entitled Some Important Limits. But before that, I owe you some proof of the claim that I made yesterday, which were a few things, like 1 over n goes to 0, and more specifically, if we have n to the p, so Francisco, I got yours is in here. Okay, thank you. If we have 1 over n to the p, excuse me, 1 over n, or if we have a reciprocal of n to some positive power, that goes to 0. But one of the claims I made was that if we have n to the power p for p greater than 0, that limit does not converge. In fact, it diverges to infinity. And what this means is something specific. All right. So how do you prove? Basically, the question I have for us is, how do you prove something's unbounded? Like, what's the definition of that? How do you? Sorry, my inclination is to close that door, but I must remember I shouldn't. So, what does this even mean? I mean, it's a symbol. We know we kind of have an intuition for what it means, but how do you define that carefully? All right, so let me just go ahead and tell you what that is. So this definition, if we say that the limit as n goes, so I've been using this informally, I think, for a little bit. Limit of a sub n as n goes to infinity is equal to infinity, right? If for any m greater than 0, right, there exists some n in the natural numbers such that what? Let's say a sub n is greater than or equal to what? M, whenever what? Or this statement you could also state as such that n greater than or equal to n implies a sub n greater than or equal to m. So the use of the word whenever gives you a way of writing implications kind of backwards. All right. Okay, so to show that this limit, so to show that this is equal to infinity, what I got to do, right? So here's some scratch work on that proof. What we need, of course, is we need to find we need to solve this inequality basically. N to the p is greater than 0, okay? Just p doesn't have to be an integer. P could be like pi or square root of 2, whatever. But basically I want to think about maybe, and I want this to be greater than m, basically, right? So all I really need to do is to solve that for p. How do you do that? Take the log of both sides. Can you take the log of an inequality? Why would that make sense, or why wouldn't that make sense? What kind of functions preserve inequalities? What's this mean? A less than b implies f of a less than f of b. Or a greater than b implies f of a. Well, I'm just writing the same thing again. Sorry. We stick with just one thing. Let me focus here. What would this mean? I mean, think about what kind of function is that? Yeah, this is a strictly increasing function. If this is true for all a and b in the domain, right? I'm really thinking of a connected domain as to not get confused about weird cases. But so how about log? Well, the natural log is certainly an increasing function, right? The derivative of the natural log is 1 over x. For x not equal to 0, that's positive. So yeah, log doesn't destroy the inequality. I can take the log of an inequality and it's still valid. The natural log of n to the p is greater than the natural log of m. And this pretty much tells me what I want to do. See, because that gives me p ln of n. Greater than or equal to the natural log of m. So I have the natural log of n is greater than the natural log of m over p. Okay, it looks to me, and then, by the way, does the exponential, is the exponential also increasing? Yeah, so I mean, I can take the exponential of this if I want. If I take the exponential of this, I get n is greater than the exponential of the natural log of m over p. Now, I suppose we could clean this up. What's the natural log of m divided by p? M to the what power? Yeah, 1 over p. And now I have just m to the 1 over p power. But maybe you would have figured that out to start with. Maybe you just looked at this at the start and just took the pth root of both sides. We could have done that too, right? This is n greater than the pth root of m. Yeah? Of course, that's equally valid and, a better way to argue, right? But I want to show you this idea that you can take natural logs and exponentials of inequalities. This is a useful thing to know about. But you got to be careful, right? I can't take the natural log of an inequality if it involves negative numbers, right? Then I'm in trouble. So context matters, all right? But here m was greater than 0, right? So it was an okay move. Okay, so this suggests to me that we need I still haven't had a chance to look it up. Do any guys have you noticed in this textbook what he uses as a notation for the next integer function? Like the greatest, sometimes it's called ceiling. I keep forgetting to look it up. See if he calls it the ceiling function. He might not. Sometimes it's called the greatest integer function. He's called it that. Well, I don't know. He may have it in here somewhere. Let's just make up our own notation then. So here's a graph of a function I'd like for us to be able to use. It looks like this. Well, I guess I got to make this so forth. So the way this works is whatever you feed to it, right? And we're going to say that this is y is equal to the ceiling. I don't know what the good, I think this is the notation for it. You won't find it in my notes. Ceiling of x. So, for example, if I look at the ceiling of 3.5, or the next, it's also called the, I think, greatest integer function, which just means pick the next largest integer, like that, right? Or 33.7, well, let's make it let me make it more clear what's going on here. 0.00001, 34, okay? So it always rounds up. It's like the ignorant rounding function, let's say. Always rounds up. I don't know, it's like a benevolent tipping function or something. I don't know. What do you want? So my point to you is that we should let this suggest to me, I want to let the n in this definition, I'm going to let n equal to the greatest integer of the pth root of m. By the way, we can also denote this pth root of m. I think it's more fun to use this notation. Yeah? Ceiling function. I won't be able to typeset that, but I can draw it on a board, and you can draw it on your test, right? I reserve the right to call this the proper notation as set forth in the book as soon as I find it. Okay, and if somebody finds it before me, bonus point. Okay, now we have everything we need to make the argument careful. So here we go. Let epsilon be greater than 0. Oh, I'm an idiot. This doesn't have an epsilon in it at all, does it? Let m be some positive integer, right? And choose n equal to the ceiling of the pth root of m. All right, then for n greater than or equal to n, that implies that n is what? Greater than, I suppose, or equal to, say what? Yeah, the pth root of m, right? But what does that say? N to the p is greater than or equal to m, right? So therefore, a sub n equal to n to the p is greater than or equal to m for all n greater than or equal to n. But this shows the limit as n goes to infinity of n to the p is equal to infinity. In other words, this proves it's unbounded. Does this sequence converge? No, right? We had a theorem that says sequence converges implies it's bounded, right? So if the sequence is not bounded, it certainly does not converge. All right, let's see here. The other claim that I made that we should check on is that the limit as n goes to infinity, right, of 1 over n to the p, all right, is equal to 0 for p greater than 0. That was the other claim we made, right? And usually, you just use these claims, right? But you might be asked to prove them separately. I mean, if I want you to actually go through these details, I would tell you so, you know. Usually the case, if I ask, you know, if something's, you know, not bounded, I'm not really looking for this kind of careful proof. A lot of times when I ask you if something's bounded or not, we're really just looking for a more intuitive argument and not one that's quite this careful. But you might be asked for this kind of argument as well. Okay, so what do we have to do? We want to so here's some scratch work. What's our goal? Our scratch, our target is that the absolute value of 1 over n to the p minus 0, we want to make that less than epsilon, given what? Given that n is greater than or equal to some particular n. And this n is generally speaking some function of epsilon. So the question is, what function of epsilon will make that happen? Right? So I'm working backwards right now. So really what I'm looking at then is 1 over n to the p is less than epsilon. So I think you see what we're going to want to do, right? So what's this? This is like 1 over epsilon is less than n to the p, right? So we can take the pth root of both sides, and we get that 1 over the pth root of epsilon is less than n, right? So I think what I should do is I should let n of epsilon, what I should do is let it be the ceiling of this guy. And the reason to let it be the ceiling is I want to make sure that, you know, it's large enough. Otherwise, I run into trouble with, it's just, well, now that I have made the suggestion, let's go from the start and see if it works, right? This is not the proof, right? This is just the man behind the curtain. Here's the proof. Let epsilon be greater than 0. Okay. Choose n equals to the ceiling of the pth root of epsilon. All right? And suppose that n is greater than or equal to n. All right? Consider the absolute value of 1 over n to the p minus 0, right, is equal to what? Well, it's equal to 1 over n to the p. Right. I guess it would have been helpful if I just kind of, even before I wrote this, like right here after consider, I said something like n is what? N is greater than what? So you know what I should do? Just to be a little bit greedier, just add 1 here, you know? Just to be safe. Then I can definitely have a strict inequality here. N is greater than what? Well, right here, right? Greater than or equal to the ceiling of the pth root of epsilon plus 1, right? That's just n again. And this is strictly greater than the pth root of epsilon. That's what I want. I want a strict, I want the pth root of epsilon to be strictly greater than n. Why? Hence what? N to the p is greater than what? Oh man, did I get flipped over? Look at that! Come on, guys! Don't let me guys. Come on, come. You guys just leave me out to dry here. You guys have got to stop me when I do something like that. Look. You are allowed to interrupt and to stop me when I do something like this, you know, right? This is part of the course. I mean, if it amuses you to watch me go on after I make an obvious error, then you're just bad people. I don't want to think you're bad people. Now, it may just because it's 8:15 and we're not awake yet. I understand that. But, you know, there's a reciprocal that's supposed to be here. 1. Right? Otherwise, I don't get what I need, right? Now, of course, this, so n over p, n to the p is greater than 1 over epsilon is what I want. Because then what? If n to the p is greater than 1 over epsilon, what does that say about 1 over n to the p? That says that 1 over n to the p is what? Is less than epsilon. So this is less than epsilon. So what I've shown then is if I choose n to be basically, you take the pth root of epsilon, you know, take the reciprocal of that, take the next integer beyond that, add 1 for good measure, and then if you assume that you have n that's beyond that, right, it follows that the distance between 1 over n to the p and 0 is less than epsilon. But that's exactly what's required in order to prove what? 1 over n to the p goes to 0, right? And that's it. That's the conclusion. This is what's needed by definition to show that. So how does the definition of the convergence of a sequence start? What's the first thing you say? Let epsilon be greater than 0, right? Just to remind you guys. So here's the definition. The limit as n goes to infinity of a sub n is equal to L. What does this mean? This is interchangeable with the following sentence. If for each epsilon greater than 0, there exists what? Okay, k in the natural numbers, right? Such that what? Such that n greater than or equal to k implies what? The absolute value of a sub n minus L is less than epsilon. Yeah, I mean, there are various other grammatical variations on this theme, but the proper definition of the limit of a sequence involves epsilons and inequalities, right? That's it. This, of course, right here, this is not the definition. This is just a notation, right? This, a sub n goes to L, also not the definition, but a notation. The definition is this right here. And that's what I was working with to prove my claim here. Okay. All right, enough about that, but I thought it was important for you guys to see some nitty-gritty proofs of something not being bounded and also this thing, since we're using it all the time, right? I'm now going to go back to section 11.4 and just start working through the examples in 11.4 bit by bit, okay? Oh, a quiz, I almost forgot. Thank you. let's see here. When does this class end? 9:30? All right. Here we go. So just to give you guys a sense of where we're going, tomorrow I will probably get back to L'Hopital's rule, and we'll wrap that up. I guess I won't get to improper integration this week, but that's okay. We still have time next week. Alrighty. I mean, I might do an example of an improper integration tomorrow, but it wouldn't be much more than that. All right, so we are in 11.4. I will do my best to show you what I can from here in our time remaining. So, as it says, some important limits. So here's number 1. If x is greater than 0, then x to the 1 over n goes to what? Goes to 1 as n goes to infinity. All right, so how do we argue this? Well, you should be happy to hear that we will not be using a direct argument from the definition, okay? I try to avoid using a direct argument from the definition as much as I can, because direct argument from the definition, as you guys just experienced, is actually kind of difficult, even for something as simple as 1 over n to the p, right? I mean, it really takes some thinking to carve through this definition bit by bit, right? It's much easier to analyze sequences and even proofs of things using the other theorems that we've already developed. So like this one, what I'm going to do is I'm going to think of, so my sequence, my a sub n is what? It's x to the 1 over n, right? So we could rewrite this as the exponential of the natural log of x to the 1 over n. You guys know that? If you have a positive quantity, you can always rewrite it as an exponential of the log of something. This is a very important and useful thing to know about, because you see what this is then. This is the exponential of 1 over n times the log of x. Now, the use of x here is unfortunate, because I want to make a comment about a function. And I usually use f of x for the function, but I'm going to have to use some other variable. Let's say f of t. Okay, so like, look at this. F of t, the following function, the exponential, right, of t times the natural log of x. Now, x here is a fixed quantity, right? X is constant with respect to t. Is this a continuous function of t? Yeah, this is a continuous function of t, right? In fact, for any real t, it's a continuous function, right? Of course, given that x is greater than 0, as we assume at the start, continuous function, right? Step number 2, look at this sequence. C sub n, right, equals to the natural log of x divided by n. This goes to what? Notice natural log of x is independent of n. It's a constant with respect to n, right? So, I mean, here I'll do some work. So the limit as n goes to infinity, so I can show you my work. I can pull the log out, right? It's a constant with respect to n. At which point, hey, we just proved this is 0, right? Because that proof works for p equals to 1, among other p. And so this is natural log of x times 0, aka 0. So what do we have? A continuous function, a convergent sequence, right? Therefore, I can use what? I came up with a name for it in the later section. I think we're going to call it the composite sequence theorem. There, now I got a name for it. But we were thinking about calling it the Pac-Man theorem, or possibly the Space Invader theorem in the later section, but it didn't seem very useful. It is also known as 11.3.12, but that seems less interesting and harder to remember. But it's the composite sequence theorem, right? It's talking about the composition of a continuous function with a convergent sequence. And what does the theorem say? It says the limit as n goes to infinity, right, of f of Cn is equal to f of the limit as n goes to infinity of Cn, just to remind you again. This is the composite sequence theorem, right? Apply this theorem. So this is the comment, okay? Returning to my solution, I'll do it in red. What's the punchline here? Hence, applying composite sequence theorem. We could call it the CST. That would save us writing. We have what? The limit as n goes to infinity of x to the 1 over n is equal to the limit as n goes to infinity of the exponential of the natural log of x over n, but that's equal to the exponential of the limit as n goes to infinity of ln of x over n but the limit inside the exponential here is 0, so we have e to the 0, exponential of 0, also known as un, or 1. And that's what we're trying to prove. See, no epsilons, no n to go beyond, right? Just use the theorem we proved last time. Not so bad, is it? I don't think it's so bad. You can disagree with me if you want. But actually, that you should have used the same logic in certain homework problems that you were faced with that you turned in just today. Let's see here. Number 2 is, any questions about this? Okay. Number 2 is that if the value of x is less than 1, then x to the n goes to 0 as n goes to infinity. Pretty much all of these results that I'm proving for you guys right now will be useful to us in the universe of examples we consider as this semester continues, all right? Until we get back to chapter 10 and you gleefully forget about this stuff for a little while until the final, right? Okay. But let's not get too far ahead of ourselves. So his proof, he says, okay, so this is on page 550. The result clearly holds for x equals to 0, all right? And he says, so if x is not equal to 0 and the absolute value of x is less than 1, you can look at the sequence. Okay, so here's the proof. If x is equal to 0, then we're done, right? Stick a fork in it. Otherwise, x is not equal to 0, and the absolute value of x is less than 1. Thus, a sub n equal to, I think, absolute value of x to the n. That's what he wants to look at. Yep. You see why, but just before I go on, why are we done if x is equal to 0? It's just 0, right? It's the constant sequence. So does constant sequence 0 go to 0? Yes. Right. What can you say about this sequence then? So if we look at a sub n plus 1 over a sub n, what do we get? Right? Which is what? Assumed to be less than 1. So what does it say? The sequence a sub n is what? Increasing or decreasing? Decreasing. Very good. Then what? Interesting. So here's what he says then. He's like, let epsilon be greater than 0. All right. By 11.4.1. What is that? Oh. Oh, man. You know, one of my heroes in mathematics is Sylvester. Sylvester is well known for, he had this trait. He would prove a theorem, some difficult theorem. And 3 weeks later, he is known to go and ask somebody if they thought that this claim was true or false. He was pretty sure it was true or something like that, and they'd be like, yeah, you proved it 3 weeks ago. So I can identify with that. See, because I was about to see, here's what he says. I mean, this statement here. Observe, epsilon to the 1 over n goes to 1, all right? As n goes to infinity. And then he's like, by 11.4.1. I'm like, what's that? Okay, well, it's this. See, let x equal to epsilon. Epsilon to the 1 over n goes to 1. X equals to epsilon fits the bill, right? Okay. Duh. Then what? He's like, thus there exists an integer k greater than 0. K in the natural numbers. Such that what? For which the absolute value of x is less than epsilon to the 1 over k. So why would that be true, guys? Why can we say that there exists a k in the natural numbers such that the absolute value of x is less than epsilon to the 1 over k? Because e to the, say again?
E to the 1, epsilon.
Uh-huh. Yeah.
1 over k is, that would converge to 1.
If I think of k as a variable, yeah. But he's saying that there exists a specific k such that it's larger than the absolute value of x. Oh, Okay. Yeah, it may just be a common. So what you're suggesting is common sense says that you can do this, right? If well. Well, I don't know if that's true though. If Ah. I'm not sure I believe that. What you said. I mean, I want to believe, but you know, I'm just trying to prove that x to the n goes to 0. I'm tired of his argument. His argument's, well, fine. I think his argument is likely correct, and whatever I'm about to do is likely wrong. But since I'm stuck on that, let me try something else. All right. Can we use something else to prove this? X goes to 0. X to the n goes to 0. Is this the composite of a function that we know and a sequence that converges? Oh, no, not really. Yowzers. What's that? Huh. I don't know, I'm stuck on this at the moment. I'm going to go on. Sorry, guys. Now, there is a proof which is very likely correct of going from page 550 to 551. I can't take ownership of it at the moment. The next one is to prove for each epsilon greater, for number 3. So, what hopefully will happen is I'll figure it out and I'll give the correct proof in the next section, and then I'll send you an email with a timestamp for it so you can see the mystery resolved. That's what usually happens. Anyway, so here's number 3. 3 says for epsilon greater than 0, I mean, the claim is certainly true, okay, guys? It's just, knowing it's true and justifying it's true are two separate things. For each epsilon greater than 0, 1 over n to the alpha goes to 0 as n goes to infinity. Hey, proof. Alpha equals to p. Did it already today. Right? That one. That's exactly what I did already. Okay. Now, what's the argument he gives, though? It's interesting to see the difference. So I argued directly from the definition earlier, right? There's a different argument you can give here that he gives us. He's like, yeah. So here's his argument. He's like, okay, so 0 is less than 1 over n to the alpha is equal to 1 over n to the alpha power, all right? And that is less than or equal to 1 over n to the 1 over p power for some positive integer p for which, for some p in the natural numbers, we can find 1 over p is less than alpha. All right. That's reasonable. And then he says, since 1 over n goes to 0, this is nice. Since 1 over n goes to 0, okay, we can all agree on that. And if we look at f of x equals to what? we want to use the composite sequence theorem here again. Thinking too hard. Look, so I'm thinking I want a function. So what I'm trying to do is we're going to use a squeeze theorem, okay? Squeeze theorem puts n to the alpha between 0, which converges to 0, right? And this thing, which we're going to argue converges to 0 here in a sec. We're trying to come to a proof that this converges to 0. So this is this sequence, 1 over n, converged with the function what? Composed with the function what? F of x is what? Blah to the 1 over p, right? So it's x to the 1 over p. Because this is this function composed with that convergent sequence. But x to the 1 over p power is certainly continuous on the non-negative reals, right? This is continuous on 0 to infinity. Thus, f of 1 over n converges to f of 0, which is to say 1 over n to the 1 over p converges to 0 to the 1 over p, which, by the way, is equal to 0. Thus, by squeeze theorem, as 0 goes to 0, and 1 over n to the 1 over p goes to 0, and 0 is less than the thing we're after, and it's smaller than the thing that we have analyzed, we conclude 1 over n to the alpha likewise goes to 0. Very sneaky what he did here. To get around, you notice I had to use this ceiling function to kind of dance around the issue that p is not an integer, right? What he's done is he's just said, I mean, my p is not his p, right? Sorry about that. I mean, it is what it is. My p is like his alpha, right? Okay, so he just traded the alpha for a reciprocal of a natural number. I could have done the same thing over there as to avoid the use of the ceiling function. But, you know, anyway, there's a second proof of this. Number 3. All right. Number 4 is a little bit more interesting. We have that for each x in the real numbers, we have that x to the n over n factorial goes to 0, as n goes to infinity, of course. Well, you mean to tell me it doesn't matter how huge x is, the n factorial wins? That's what this says, basically. Right. So here's his proof. Ooh, something sneaky happens here. Let's see if we can follow along. So what does he do? He says fix any real number, so fix x. Right, so that's a constant. I mean, that's a fixed real number. And choose some k in the natural numbers such that what? The k is larger than the magnitude of x, okay? So if x was like 30.7, you could choose k equals to 31. If x was 1,000,000, you could choose k equal to 1,000,001, or I mean, so forth and so on. It's pretty clear you can do that, right? And then he says, okay, so consider for where are we? N greater than k plus 1, all right, we have the following set of inequalities. So this is k to the n over n factorial is equal to what? Ooh, this is very sneaky. Check this out. So he's gonna use this k. So first of all, he splits off a k to the k over k factorial. What's left? Think about this. If you split off a k to the k out front, how many k's do you have left? You've got, well, a bunch of them, right? He splits off one more k over n out here. All right, so if he does that, how many k's are in the brackets? You can count, right? This must be how many k's? How many factors here? Yeah, n minus k minus 1, right? Of those. And what's he put downstairs? This is just an equality, so you follow it, right? It's got what? So this k factorial has got k times k minus 1 times 3 times 2 times 1. So this is just going to count all the way up. This is k plus 1, k plus 2, you know, and the last one here would be n minus 1. So all we've done here is just to rewrite the n factorial explicitly as a product of factors. And then he does something rather sneaky. This is less than what? He says this is less than k to the k plus 1 over k factorial. Times 1 over n. And he says since k is greater than the absolute value of x, we have that 0 is less than the absolute value of x to the n over n factorial, all right, which is less than k to the n over n factorial, which is less than k to the k plus 1 over k factorial times 1 over n. And then it follows, since k is fixed, as n goes to infinity here, by the squeeze theorem, we get the desired result. So the question then, my point to you is, once you have this, right, you can write this, 0 less than this, less than that, by what's above. And then by the squeeze theorem, we're done. So the question remains, of course, why is the thing I haven't explained true? Why is this actually true? Is that your question? Yeah? I haven't explained it yet. I just wanted to say, once we know that, we're done. Everybody agree? Because once I know that this is less than that, then I can replace k to the n over n factorial with this, right? K is fixed here. Right, k is just a fixed integer which is larger than x. It doesn't depend on n. So as n goes to infinity, this goes to 0, that goes to 0. We squeeze the thing we're after to 0 as well. So can you guys tell me then, why is this inequality valid? What are we assuming right here? That says that n minus 1 is what? Greater than k. So let's see here. K over n minus 1 is what? Let's see here. So let me write this the other way. I'll help you out. K is less than n minus 1. So this factor right here is less than 1. So if I replace it with 1, I've made the thing larger. Right? And how about this? K over k plus 1, k over k plus 2. I've got a number divided by a number smaller than that number. Is that, if you replace that with 1, what have you done? You've made it larger. Right? So replacing this square bracket with 1 gives us a larger quantity. Because every product, everything in here, k over k plus 1, k over k plus 2, k over n minus 1, every one of these is something that's smaller than 1. So if I replace it with 1, I've got something larger. And once I have that, squeeze theorem finishes it for me. The same logic was required to do that homework problem you guys had. The 4 to the n over, what was it, 2 to the n over n factorial less than, a very, very similar argument is needed there. All right. And let's see here. Next is that the ln, well, natural log of n over n going to 0, we can prove by L'Hopital's rule, and I'll do that. So I won't do that. Oh, actually, hey, that's it. That's it for the things I want to prove in this section. Everything else in this section I will derive with L'Hopital's rule maybe tomorrow. So there's no need to do it this way. Okay? So with that, I will give you your quiz. And then I will harass you to give you back homework as you're taking your quiz. I hope you don't mind. Some of these questions are easier than others. Like, where did you take calculus 1? And how? That's pretty easy. So like the answer would be engineering 131. And, you know, I guess the how is here. Maybe you took AP calculus at your local high school or whatever. I mean, I'm looking for kind of location for question 1. Or, you know, I took calculus 1 online or whatever. And then when, of course, is also important to me. The next problem is just a differentiation problem. I promised a student in another class yesterday I'd ask you guys this because he couldn't do it. So I wanted to make him feel better because I have a suspicion some of you can't either. And sorry, it's an experiment. I'm curious. Problem 1. That should take you all of like 5 seconds. Problem 2, we talked about today, didn't we? Oh no. Phew. Okay, that was close. I was about to get no data at all from question number 2. Golly, you guys gotta stop me. Problem number 3 is actually kind of like one of your homework problems. So. When you're done, you can leave. Sorry about the error in the